Hello, humans and the environment. Welcome back to our lectures. Today, we are going to be talking about some basic concepts in environmental science that will help us as we approach this class throughout the semester. So some of this will be reviewed in future lectures, especially the lecture on Suzuki and Dressel's piece coming up in a couple of weeks. But today we'll be talking about population growth and economic growth first, and then we will talk about resources, what resources are and what types of resources there are. We'll talk about environmental problems and their causes, and we will talk some about systems and how scientists analyze and understand complex systems. So today's lecture is derived from this book, Environmental Science, Working with the Earth by Tyler Miller. And it starts out talking about population growth. So what is the problem with population growth? Well, the problem is that our population is growing exponentially. And you can see here the problem with exponential growth is that it starts out very slowly over millions of years. You can see on this timeline from the time we were hunters and gatherers, we basically had very low numbers just creeping up, barely creeping up through millennia. And then after a quick dip during the plague, the population just shot up. Here you can see in this diagram, it shot up to unprecedented numbers. We don't really know how far it's going to get because we're living through this change, which happens largely as a result of the Industrial Revolution and improved medical practices and sanitary practices, and it's just allowed our population to explode. That's a problem because the Earth can only support a limited population. It's a finite planet, and so we cannot keep growing exponentially indefinitely. So there's no telling really where it's going to max out. But as the population grows, we put more and more of a strain on the Earth's resources, and that is a problem if we want to live sustainably indefinitely. We also have this concept here called doubling time, which is the amount of time it takes for a population to double its size, which I think they estimated was around 53 years in our case. And I should also point out that the rate of growth of our population has slowed somewhat recently, which has other problems also that go along with it, including a diminished workforce, younger people not being able to support an aging population. But you can look for more current data on the current rate of population growth and see where we're at. I think we just recently crossed 8 billion people last year, very recently. So one of the overarching problems of how we relate to the environment, how we're going to impact the Earth as our numbers continue to increase exponentially. Then we have economic growth, which is defined in this text as an increasing capacity to provide people with goods and services measured by these three different criteria: gross national product, gross domestic product, and gross world product. So gross national product is the market value of everything produced within and outside of a country by our country's businesses during the year. So all our the goods that are manufactured here and the value of the goods that are also exported to other places around the country. Gross domestic product is the value of goods and services that are produced within our country. And gross world product is the market value of all the goods and services produced in the world each year. So we use GNP, gross national product, and GDP, gross domestic product. Often we use this to think about the progress that a country has made, or sort of how well we're doing. But it's important to keep in mind that these metrics do not consider, one, the distribution of wealth within our country. So you could have some very wealthy people buying expensive goods and services while most everyone else lives in poverty and contributes very little to our GNP, and still have a very high GNP because of that imbalance and because of the impact of the wealthiest people in our country and how money flows from those people. They also GNP and GDP do not count lots of beneficial transactions that don't have any monetary exchange to accompany them, such as caregiving, taking care of kids or elders, exchanges that go on between friends and loved ones, things we do for ourselves, tending a garden or building a house for ourselves, things that aren't valued monetarily don't count towards our GNP or GDP, but still may improve the quality of life for people in our country. Another thing is that GNP and GDP don't take into account human well-being or the status of our environment. So if you have a society of lots of depressed people and a pharmaceutical company makes a drug that can treat that depression, then that will actually increase our GDP because of the money that's spent treating depression. So you can see how using GDP and GNP as a measure of how well we're doing doesn't really add up because of these things that are missed when we calculate our progress based only on how much money changes hands. So it may count these things like pollution, crime, sickness, mental illness, and death as benefits, since money must be spent to deal with these problems. I've also included here a graphic from the text, which you can look at on the PDF of the reading itself more closely. But what this shows is in the top model, a more traditional model of the market economic system that shows it as a closed circle where you have goods and services and money being exchanged between businesses and households as if they're the only parts of this equation. And then in the second picture on the bottom here, it shows what a more thorough accounting of our economic system would look like if we included the natural services provided by our ecology, the ecosystems that we're part of, on which our economic systems are all based. Okay, so we don't live in a vacuum. We don't exchange money with businesses and buy stuff in a vacuum as if we aren't deriving everything that we own and accumulate from the earth itself. We are living on the earth and within ecosystems that provide the resources that we exploit in our economic system. So this is a more complete picture that shows how our economic system depends on the natural systems that we are a part of and that we live within. Another important concept, I think, from this textbook is the idea of internal and externalized costs. So if you buy a computer, you pay a certain amount for that computer, and the amount covers the cost of mining the minerals that go into building that computer, paying for the labor that actually built the computer, paying for the corporation who makes the computer to have buildings and overhead. You're paying for all that. All that is built into the cost of the computer. But there are a lot of additional costs that are related to creating that computer that you don't pay for as a buyer. So for instance, if one of those mineral mining operations that take something from the environment to build your computer, if one of those operations increases pollution around the area where it's happening or causes people to get cancer nearby because of the way the factory operates, then those people who live in that community might be impacted by that operation without benefiting from the computer itself, without ever seeing the computers that are made from that operation. And if they if they have higher cancer rates or lung damage from factory pollution, then they end up paying that cost through their medical bills, and maybe insurance pays for some of that cost. And maybe some of those things impact people in the future who don't even exist yet, because pollution sticks around. And you don't pay for any of that when you buy your computer. Those are all what we call externalized costs, the costs that actually are part of the creation of the computer, because they are costs that are, go along with creating that device, but they're passed on to the public, to people who live near the factories where those things are produced, and you don't pay for them as a person who's buying a computer. So I've heard estimates as much as like $200 for a hamburger if we actually built into the product all of these externalized costs and pass those on to the consumer. So it's an interesting question of whether we can use pricing in that way to really account for the damage that we're doing ecologically by our resource consumption, and whether we should be paying $200 for a hamburger if that's what it actually costs to create the hamburger, if we consider the costs to the public, to future generations, etc. So that is another concept that I want to make sure you understand. Okay, so something to note about when we think about population growth, here are some statistics about the difference between developed and developing countries in terms of their resource consumption and their contribution to the world's population. Developed countries have about 85% of the world's wealth and income. That's vast majority. We use about 88% of the Earth's natural resources, and we generate about 75% of the pollution and waste in the Earth. So important things to keep in mind, and at the same time we comprise only about 20% of the world's population. So already we can see that the resources in the world are being used, are unfairly divided. We don't all have a fair equal share of the world's resources in different countries. In the US, we use a much greater share of the world's resources than in many other places. Now, relatedly, more than 95% of the projected increase in the world's population is expected to take place in developing countries. So while we have lower fertility rates in more developed countries, our resource use does not correspond to that. So even though there are vastly more people in developing countries, the resource consumption of people in developed countries just far outstrips what is being used by people in developing countries. Okay, so this is an important little graphic here. What it shows is that the total environmental impact of a population is a function not just of the size of that population. So the problem is not just population growth, but it also has to do with how much each person within that population consumes, and how much it costs to provide each member of that population with what they consume. Okay, so the impact of what the particular things that we're consuming on the environment, plus how much we consume, and also how large the population is. Okay, so moving on to resources. A resource is anything derived from the environment to meet human needs and wants. So examples: food, water, shelter, goods, transportation, everything that went into making your laptop, everything that we use comes from the earth, and all of those things are considered resources. There are different types of resources. If we think just within a human time scale, some resources are perpetual. That means they'll last basically forever. I mean, not really forever, because the sun is going to die at some point, but it's so much further into the distant future that it's not even relevant to the length of time that humans are actually gonna be on the earth. So we consider those to be perpetual. There are renewable resources, which can constantly regenerate themselves. And there are non-renewable resources, which means there's just a limited amount, and you're using it up and it won't be replenished in anything like a time scale that we would need for it to be replenished in order to count it as a renewable resource. Okay, so again, perpetual energy sources are being continuously renewed. So that includes energy from the sun, wind, tides, flowing water, which we harness for electricity through damming it, etc. Renewable energy that's replenished fairly rapidly within a time scale that we're considering, such as forests, grasslands, wild animals, fresh water, fresh air, and fertile soil. And the thing about renewable resources is that they can be renewed infinitely as long as we only use them at a rate that they can renew themselves. So if we deplete them faster than they're able to be replenished, then we start to see the resource being degraded and diminished. Okay, so the sustainability yield here, another term to note, is the highest rate at which we can deplete a renewable resource indefinitely. Okay, so as long as we limit the amount of lumber that we take from forests, for example, we could go on having lumber indefinitely, and future people could enjoy lumber also, could enjoy, having wooden houses and all the things, furniture, toys, all the things that we use lumber to build. We could have that indefinitely. It would just keep replenishing itself as long as we limit the rate at which we're consuming it. But since we're consuming it at a much higher rate than what it's able to replenish, we're degrading forests, we're depleting forests, and eliminating the ability of the forest to regenerate. Okay, environmental degradation occurs when we deplete a renewable resource more quickly than it can be replenished. And you can see page 11 on the tragedy of the commons. So the tragedy of the commons is this idea, and I'll mention this again in a future lecture, but this idea that we have some kind of resource like clean air, right? We all need to breathe clean air, and we've seen that need, that the ability to breathe clean air be jeopardized over the summer. There have been like at least 12 days when the air quality was so poor that we were advised to all stay inside. But so you take something like clean air, and how do you use up clean air? Well, you pollute it, right? And then there's no more clean air unless you pollute it just a little bit at a time so that the pollutants can be eliminated through natural processes. But if everyone is polluting the air and thinks, well, if I only pollute it a little bit, then it won't really matter because I'm just one person. It's not a big deal if I just use a little bit of the clean air and take a little bit away from whatever my needs are. But then everyone thinks like that, and so the resource gets used up, and we don't have clean air anymore, so we have to stay inside. But the tragedy of the commons is this idea that everyone sort of takes what they need, thinking it won't be a big deal if they're the only ones that do it, but then everyone thinks like that, and then the resource gets used up, so we don't have clean air anymore. Okay, and finally, there are non-renewable resources which exist in a fixed quantity, such as coal, oil, natural gas, minerals. And the way to, save non-renewable resources so that we can keep using them as long as we want to, is to reduce, reuse, and recycle, right? In order of importance. So reducing is really the most important part of this equation. We have to limit the amount that we use up these resources. It's far more effective than reusing something, or recycling it is just not creating it in the first place, not using up the resource to create this thing in the first place by just reducing the amount that we consume. And one way or another, we're going to be reducing the amount we consume because our current rate of consumption is unsustainable. So if we do that sort of proactively in a time where we can decide what's most important to us, that's really an optimal situation rather than just being in such a desperate circumstance that we don't have the resources that we need any longer to keep living. Okay, and next in line are reusing and recycling. So reusing should always come before recycling. If you have a bottle, there's lots of different uses for that. There's a place in Durham now that collects old jars and provides groceries, all in reused containers that they sanitize, so they don't have any new packaging. They don't purchase anything like that. All of the whole grocery store is just like a big bulk section. You can get a ton of stuff there, but you either bring your container or you get one from the store, which somebody has donated that's already been used. Okay, so reusing, and then finally recycling, when we take the products that we've made and, send them to the recycling plant to be made into some other product, which is also energy intensive and much less ideal than just reusing something or not even making it in the first place. Non-renewable resources are economically depleted when the cost to extract them exceeds their economic value. Okay, so we're never going to get all the oil out of the ground. There's going to remain oil in the ground that we're not ever going to be able to extract, because extracting it becomes more and more difficult as the resource is depleted. And at some point, it's just not worth it to extract that oil. It would cost more money to get the oil out of the ground than what having the oil contributes economically. So you can see this curve here, which shows that we find oil that was, long ago, and our rate of extraction increases, but then it peaks at a certain point, gets to the top of this curve, and that's the most oil that we'll ever be able to extract. From then on out, after that peak, then we get diminishing returns. So it costs, again, more and more money to extract the remaining oil, and at some point, where this dotted line is, you can see 80% used up. It's just too expensive to keep extracting oil because it takes too much effort to get it out of the ground when there's not as much left, and then it's not worth it. So in many places, our oil extraction has already peaked, and some people think that globally our oil extraction has already peaked, and that we're now, on the downside of this curve. Okay, so an environmentally sustainable society satisfies the basic needs of its people without depleting or degrading its natural resources, and thereby preventing current and future generations of humans and other species from meeting their basic needs. Okay, so think about Ishmael, right? We can be the first without being the last. So humans can make the world so that evolution can continue indefinitely, so that we can continue to have complex organisms and life on Earth, human life on Earth, and whatever is going to follow us in evolution indefinitely. We could just go on using Earth's resources in a limited way so that they will last forever. We will never use up the forests if we only use them at a particular rate, but much less rapidly than what we're actually using, than the rate that we're actually using them at. So another way to think about this is that living sustainably means living off natural income only rather than depleting natural capital. Okay, so you can think about capital and income like a bank account, right? You have your savings account, and then the savings account is generating interest. If you only live off the interest, you sort of lower your sights, limit how much money you spend, then you can go on living off that interest. If you have enough provided, then you can go on living off that indefinitely. But if you start to use up your savings themselves, then you get less interest as a result, and eventually your savings account gets depleted. Okay, so we have a certain amount of resources, a certain amount of goods that are provided to us from the earth, and as long as we live on what they can sustain at a rate that can be sustained, and the resources allowed to replenish themselves through the natural processes that are part of the earth, as long as we do that, we can go on living here indefinitely, and that's a good thing. I want life to continue, right? I want humans to not bring about the end of the world, right? We want life to continue beyond us, and as long as we keep our consumption within limits, then we could have that. But the way we're living now doesn't allow for that. Okay, so let's look at some environmental problems. They list air pollution, water pollution, waste production, biodiversity depletion, food supply problems, severe weather, and I've made a note here to check out figure 111, which elaborates on some of these. What's important to note about these problems is that the causes are not just the size of our population, right? It's not just that there's too many people taking from this system, but also it matters how much we're consuming, all right? So you think again of those stats about developing versus developed countries, and how while the vast amount of population growth is happening in developing countries, the majority of resource consumption is happening in developed countries like ours. Okay, so the causes of environmental problems include both of those ideas, both the size of the population and the rate at which the population of the world is increasing, but also not population doesn't explain by itself why there is an environmental crisis. We also have to consider the amount that each member of that population consumes. And these play out differently in developed versus developing countries. So you can think back to that graphic that shows that environmental impact is a function of population size and rates of consumption. And this astounding fact, which we are going to talk much more about in the essay called Bigfoot by Suzuki and Dressel. The average US citizen consumes 100 times as much as the average person in the world's poorest countries. That's the statistic they give in this textbook. I've seen that slightly different statistics in other texts, but they all agree that we used vastly more than the average person in a poorer country. And you can check out pages 13 and 14 for more information on that. Okay, so when we're thinking about environmental problems, and this sort of gives more content to the ideas that are originally discussed in Ishmael in this class, 3 major cultural transformations have had different impacts on the environment. So the agricultural revolution, the industrial revolution, and the information and globalization revolution, which is currently underway and really just began. So the agricultural revolution was when we moved from being hunters and gatherers, roughly 10 to 12,000 years ago, like Ishmael told us, to settling and farming, right? Settling down in particular places and farming the land. And when we were hunter-gatherers, we didn't have much of environmental impact because whatever environmental impact we had, we just moved to a different place, and the original place could sort of regenerate and heal itself from our presence. But the agricultural revolution changed that, and we started to have more of an impact on nature. And then with the Industrial Revolution, which began really just like an instant ago, if we take that broader perspective of the history of humankind, our environmental impact increased dramatically. And you can see that original population curve that I showed on one of the first slides. That's where our population really started to explode. So the Industrial Revolution involved making goods in a widespread fashion from a central location, right? So we can, instead of just having localized communities sharing and trading goods that they create themselves, when at the beginning of the agricultural revolution, as that moved on, the Industrial Revolution led us to start mass producing goods for a huge population, right? So we concentrated our efforts into factories. People moved into cities to take jobs in those factories, and we started just mass producing all the goods that you have right in your apartment or your dorm room, right? Everything around you right now is possible because of the Industrial Revolution, because we were able to start mass producing goods. And that was when our environmental impact increased significantly, because those factories led to pollution. The amount of goods we were creating and producing just totally outstripped what had been happening previously, and we started extracting more and more resources from the earth at rates that are unsustainable. So now we are in the information and globalization revolution, which is a change in how we get information. So we have the internet all over the place. You can talk in live time with somebody in India, right? That was never possible before this revolution. I didn't have email in high school, right? That wasn't around when I was in high school in the 90s. But now it is. Everyone has an email account, even my 11-year-old niece, right? So the rate at which we can exchange information, and the idea of globalization is just that we're becoming increasingly interconnected across the globe. And so we can talk to people across on the other side of the globe. We can make goods to provide to people on the other side of the globe, but more commonly, they make goods that we consume, right? Globalization allows for those goods that we consume, all the stuff that went into making your computer or your shoes, your tennis shoes, or whatever, your shirt, was probably made very far away from us and then provided to us through an intensive process that included moving that stuff around the world. Globalization also increases the spread of infectious disease, which is something we're going to talk about next week. And so this is the revolution that's currently underway and just began. And it's sort of a food for thought, an interesting question of how this is going to change our environmental impact in the long term. And I think we can also think about AI in this section. How is artificial intelligence going to, as a part of the information and globalization revolution, how is that going to change our relationship with the environment and our surroundings? And that we won't really know until it all plays out. But we're in a really fascinating moment here with AI sort of taking off in recent months. Okay, so the next thing I want to talk about before I leave you for today is complex systems, because ecosystems are complex systems. There are so many components of an ecosystem. A system is defined in this text as a set of components that function and interact in some regular and theoretically predictable manner and can be isolated for the purposes of observation and study. So if you think about physics, right? How fast does a ball drop, right? That's a simple question. We can just, if we had good enough cameras to watch it in slow motion and get our good enough timing devices, we just watch the ball drop and calculate how fast it's dropping, right? But if we want to study an ecosystem, there's just so many components, right? The soil, the animals in the ecosystem, the sun's energy and how that's, the gases in the atmosphere that are affecting how the sun's energy gets absorbed by the earth. So many complexities when we start to have more than one component all working together. Okay, so I didn't finish this definition, so let me just say that a system is a set of components that, one, function and interact in some regular and theoretically predictable manner, and two, can be isolated for the purposes of observation and study. So when scientists study systems, they create mathematical models to try to analyze how those systems work and also to make predictions about what will happen in the future. So an example of this mathematical modeling is this study I read about in the Washington Post, in which scientists discovered that if Phoenix experienced a power outage and a heat wave at the same time, and we know about these heat waves from this summer. I hope you've been watching the news and seeing how hot it is and how many people are dying from heat exhaustion, heat stroke. But if these things happen together, so people in Phoenix who've been experiencing like 120 degrees, I think temperatures exceeding that around the world. But if that happened in Phoenix, they focus on Phoenix as a finite ecosystem within itself, a system with many complex components, but just focused in that city. Thousands of people would die, and it says here roughly half the city could end up in the emergency room. Okay, so part of that system and analyzing that system is also understanding how many people the medical system can accommodate who are in a medical crisis, right? So if these things happen at the same time, this is what would be the result according to these mathematical models that people created to analyze this complex system of a city facing increasing temperatures. Okay, so systems theory, understanding complex systems, is really useful for everything that we're going to do in the rest of this class, because we're studying a complex system with complex interactions between individuals within that system. So ecosystems that we're studying, the relationship between humans and the environment, looking at how scientists understand complex systems can give us tools for better analyzing our current situation, how we relate to the world around us. Okay, so some notes to make about complex systems. So systems undergo change as a result of feedback loops. A feedback loop occurs when one change leads to some other change, which either reinforces or slows the original change. Okay, so you have this system, right? Many components working together. And when one thing changes, it affects other changes within that system. And we can understand those changes as either positive or negative feedback loops. So in a positive feedback loop, one change in a system causes a further change in the same direction of that system. So what's an example? I like to use this example of eating well and exercising, right? Because if you go out and exercise, at least in my experience, chances are that when you come back from exercising, you're not going to want to eat junk food. You're going to want to eat healthy food. Working out affects your appetite, right? And it affects what kind of food you want to eat. This is something I've experienced anyway. Maybe you haven't experienced the same thing. But the good thing is that when you eat better, you feel better and are more likely to want to engage in physical activity. Okay, so that's a positive feedback loop to good health. It's good news if you're in a slump about your physical health, right? Because if you get up, go for a walk, go for a run even, you'll come back feeling good and you'll want to put better stuff in your body, and putting better stuff in your body will make you feel more active and like being active some more. And it's just a positive feedback loop. It just goes on until you get healthier and healthier, ideally, right? In a negative feedback loop, one change leads to a lessening of that change. Okay, so the examples I give in the text have to do with a thermostat, right? We can talk about heat in a building, and they also talk about heat in your body. So let's talk about heat in a building first. So, or air conditioning, right? So I've got my air conditioning on right now. It's set to 78 degrees. I'm looking at my thermostat over there. What that means is that the sun is out, it's shining down on my house. It's much hotter than 78 degrees outside. And so because the air conditioner is not running right now in my house is heating up because the sun is coming down on my house, warming up the atmosphere around my house, warming up my roof, right, the top of my house directly, and all that heat is coming into the house, or much of that heat is coming into the house. And when it gets to a certain point, when it gets hot enough, what's going to happen is the thermostat is going to notice that it's too hot because I want it to be 78 degrees in here. And so it's going to turn on my air conditioner. My air conditioner will kick on, and then it's going to cool down, right? The air conditioner is going to cool down the house. And then when it gets to 78 degrees, it's going to stop, right? It's going to stop cooling down the house because I don't want it colder than 78 degrees. Okay, so what's happening? The thermostat makes sure that there's a negative feedback loop here. It gets too hot, thermostat kicks on, brings the temperature back down. When it gets too cold, the air conditioner will turn off, and then it will start to get hot again. So it just sort of goes back and forth and keeps itself in a nice balance at 78 degrees. Okay, unlike that, if it were a positive feedback loop, like they give the example of climate change, right? Rising temperatures. So it gets hotter outside in the atmosphere, more ice in the ocean melts. Well, when more ice melts, the ocean becomes more absorbent of that heat energy, right? And so even more ice melts after that because the ocean gets hotter because the ice helped keep some of that heat and deflect some of that heat back. Now the ice is gone, so the ocean gets hotter and then remaining ice melts more quickly. Okay, that's a positive feedback loop to rising ocean levels, right? Rising sea levels and everything getting hotter and hotter and hotter. In your body, okay, you have a combination of positive and negative feedback loops. So it's just thinking about temperature regulation within your body. So it's kind of like a thermostat in my house, right? I have a system, we all have this biological system, that when our body heats up, things kick on to help cool us down. Like we sweat, right? And that evaporation of the sweat off of our skin cools our body because it takes heat to evaporate, and that heat energy is lost through evaporation, and then our skin feels cold. If you put a little drop of water on the back of your hand and just let it evaporate, you'll feel your hand cooling, right? That's how your body's temperature system works. That's why you sweat, to cool down your body. And so you get too hot, your sweat kicks in, right? You start sweating, and then your body cools down. And if it gets too cold, you stop sweating, right? Once you're cooled down, you don't sweat anymore. Okay, so that you don't get too cold either. So if you get too hot, then the system is overridden, right? It can't handle that change. And you get too hot, you overheat. Like if there's a heat wave and you're outside and you're not hydrating, and it's just too hot for people shouldn't be outside in that heat, then it overrides your system. You don't sweat anymore to cool you down, or you do sweat, but it can't even keep up with the amount of heat that's coming into your body and that's heating up your body. Then your metabolic processes speed up because your body's warmer, and that makes your body even hotter. Okay, so in the text they say this ends when you die of heat stroke, right? You just get hotter and hotter and hotter because that system that created some kind of homeostasis, some kind of balance through a negative feedback loop, kept you at the right temperature. But once that there's too much heat that system can't operate anymore to keep you cool, then you just get hotter and hotter and hotter until you die, because you can't live in that environment. Okay, so that's positive and negative feedback loops. I'm going to mention this again in another lecture, but one thing to note is that positive does not mean good in this case. In fact, positive feedback loops are often very bad because it means that the system is just running out of control, right? It's not in a stable place. Whereas with a negative feedback loop, it's much better because you keep your body at the right temperature, for example. Okay, so important stuff to understand about positive and negative feedback loops. And this is all related to synergy. Okay, so synergy is when a synergistic interaction occurs when two or more processes interact so that the combined effect is greater than the sum of their separate effects. Okay, so what's an example of that? Well, imagine that your apartment is really messy, right? And you do some cleaning for an hour in the morning at 10 a.m. while your roommate is out of the house. And then your roommate comes in at 12 o'clock and does some more cleaning. And at 1 o'clock, you've cleaned up the apartment somewhat, right? And it's still somewhat messy, okay? But imagine that you and your roommate have such great energy, right? Just a great dynamic, a great chemistry with each other, that you decide, well, let's clean the apartment at 11 o'clock, right? And so you come together and you put on some music and you just feel good working with somebody else, right? And you even if you only work for an hour together, you might be able to do a much better job together just because you're sort of riding off the energy of one another, and you're pumped by each other's presence, and you're getting stuff done, that you end up working for the same amount of time, both of you, but since you're doing it together, you just have a much greater impact on the cleanliness of your apartment because of that synergy that's created when you work together. Okay, so there are lots of examples of this when you think about how being part of a group or working with others can make you more powerful than you would be separately, even if everyone who's part of that group were doing the same amount of work. Okay, so that's synergy, and synergy can be good or bad, right? It can be bad when we think about the way that harmful environmental impacts work together to create results that are worse than each of their components separately, but taken together, like the sum of their separate components. So an example of that would be like having cooling centers, for example, during a heat wave, and it's also a pandemic, right? So if you got this terrible heat wave, people are going to die in a heat wave. Heat waves are the worst natural disasters in terms of the consequences for human health. But if you have a heat wave and a bunch of people die, and so you put up these cooling centers, well, if it's pandemic, then you're also going to have to deal with the spread of infectious disease when you bring that many people together. Okay, so the negative impacts are magnified because those two things are happening at the same time. Whereas if you just had them separately, if you had a pandemic, but you could keep people more separate and didn't have to crowd them into an arena or something to cool them down, then you would be able to keep the disease spread under control. And if you had the heat wave without the pandemic, then you would be able to use the cooling centers without increasing the spread of infectious disease, right? So the impacts of both of those things happening separately, even if they both happen, would be less than when they happen together, and it magnifies those impacts. Okay, so this is so important for understanding how to think about this class, because synergy can be harnessed, right? We can use synergy, this concept of synergy, to maximize our impact. If you think about, think about maybe you've played softball or baseball or something, and sometimes, like, you could swing, right? You miss the ball, you're just expending all that energy and nothing's happening, right? Even if you hit the ball, right? If you don't hit it exactly right, it can feel really like heavy on your hands. I've had this experience. You hit it and it doesn't go quite right. It just feels like heavy and clumsy, and you don't get the real powerful punch that you would hope for. But sometimes when you're playing softball or baseball and you hit the ball just right in the right spot, the same amount of energy from those last hits that didn't go very far can really launch that ball really far. Okay, so you have to use leverage points. They mention leverage points briefly in this text, but you have to find exactly the right place, right? The right way to bring that force. And then you have the biggest effect, okay? So we can use that not only to think about the ways that the consequences of our environmental impact, the negative consequences, and how they exacerbate one another. And in another lecture, I'm going to use the term cascading consequences, which is related, right? The way that consequences work together and impact each other to make for worse consequences, right? But you can also think about those things not just in terms of the negative effects, the bad stuff, but also the good stuff, right? Because we can utilize that understanding to input energy into that system in the spirit of solving some of our problems. And we can use that understanding to maximize our impact and to have the greatest impact by utilizing those leverage points, hitting the ball just right so that it really shoots out into the air and you feel like so strong. I hope some of you know what I'm talking about, at least, but when it comes to baseball. But we can also do that with the environment, so that when we use our energy to try to change the world, to try to make things better in our environment, we can do that strategically and not just waste all this energy sort of in different ways, but actually focus our energy and work together and find where those leverage points are that are really going to get us the biggest bang for our buck. Okay, and I think this is the last slide. The law of conservation of problems, another useful concept that we get from this chapter, is that solving one problem often, even usually, creates other and unanticipated problems. So in Australia, they had a beetle problem. Beetles were destroying their crops. They brought in these cool frogs that ate the beetles, but it turned out, they brought in the frogs to eat the beetles, but it turned out they didn't even... they weren't awake at the same time. Like, the beetles were awake during the day and the frogs were nocturnal, or vice versa, but they never met. And so the frogs, in practice, in theory it was a good idea, but when they actually tried to implement it, it didn't work, and they ended up with a frog problem and a beetle problem, right? Or you use fertilizers to grow more crops, so you have the problem of how to increase crop yields. You bring in these artificial fertilizers, and you get these really amazing crop yields, but then the fertilizer pollutes the water source and runs downstream and causes disease and harmful consequences to the communities living downstream from where those fertilizers were used. Okay, so another aspect of comprehending the complexity of our situation and how we're going to approach it. So I hope you have enjoyed this lecture, and as always, if you have questions, please don't hesitate to ask, and I will see you next week.